Oh, it's actually really cool. There's like so many people actually here. I didn't expect it for Vancouver. I feel like I don't associate Vancouver with like having a big systems community. Um, which is anyway. But yes, let me share it. I want to present. Does this work? Can everyone see? Okay, awesome, cool. A quick gauge. How many people here work in search or like know anything about search? Like
No, if it's
5 people, 6 people, like 100%? Okay, cool. Anyway, yes. My name is Morgan. I work at TurboPuffer, and we are a search engine composed of a single Rust binary and object storage. That's it. There are no other dependencies whatsoever in the system. That's it. We support mostly vector queries. So this is like k nearest neighbors over high dimensional vectors. We also do full text queries like EN25, and we do scans. Aggregations are coming soon, hopefully like in a few weeks. Yeah. TurboPuffer is roughly just over a year old. We have 7 people, mostly also ex Shopify. The last year has been kind of insane. We've gone from 0 to roughly about 1,000 queries per second and about 40 billion documents. And we do roughly about 2 billion documents a day in writes. And that's a photo from us a few weeks ago, actually, in Ottawa. So why we actually do what we do? I asked our CEO Simon this question, and he was like, "Oh, we should use the marketing slogan that we use on our website. The cost of search is limiting product ambition." It's good for the website. It's not good for like a fun systems meetup. So the actual real answer is that we're searching a lot more these days, right? Specifically for feeding context into large language models. And what's interesting is that the entire game of search has changed. We're now using vector embeddings to search as opposed to doing full text search, which is sort of the more traditional boomer type search. For example, traditionally, right, the query red dress was kind of this like really difficult query process if you wanted to return results for burgundy skirt. That's like a really difficult thing to do in like old school keyword matching, but it's like absolutely trivial in vector land. And there are really not too great options in terms of like a database actually built for this world. In terms of that also, I mean, search has become really, really complex, right? You have this like massive, massive systems that have a lot of data in them. And I don't think a lot of the new systems are really ready for the just pure volume of data that is the vector search world. Yeah. Also, it's really cool that like search is uniquely qualified as a problem to like have a small team actually be able to have a large impact. Like a small team can do really cool things in sort of the search world. So if you want to sort of go into how do you make search cheap, right? A lot of the existing systems, database-wise or whatever, are sort of here, right? You have largely backed by SSDs and memory caches, right? And in the full text world, that's fine, right? A terabyte of text is a lot of text. But a terabyte of vectors in this sort of new search world is 120 million vectors, which is not that much, right? So in order to actually have economical search in 2024, you almost need to go sort of down the cost chain storage-wise and go all the way down to the lowest possible medium, which is object storage. Now, the question is, can you actually build database object storage? 2 or 3 years ago, the answer would be no. But as of late, there's been some pretty decent innovations in terms of like what they support in order to actually make this possible. So obviously you have NVMe on AWS in 2018. It's a big step. 2020, S3 is consistent. It helps to have consistent object storage and making a consistent database. And finally, S3 does not have this yet. Hopefully soon. All the other providers have it. GCS has it, Azure has it, but it's an operation called compare and swap or conditional writes. And sort of, I'll talk about this a bit later, but generally it's like a big simplification factor for us. You don't need a dedicated consensus layer if you can do conditional writes. Speaking of writes, how do you do them? At TPUF, we have this sort of like idea of a namespace. So in these sort of vector workloads, you very often have what's called like a natural sharding key. So for example, per user. And usually users shouldn't be searching over other users' data. Generally doesn't go very well. So on object storage, right, we map each namespace to a prefix on object storage, like a folder basically. And the way object storage works is that you can have essentially as many of these prefixes as you want. It doesn't matter. So you can just keep on adding namespaces horizontally and no problem whatsoever. And obviously, sort of like, as you'd expect, a write, in this case, is just us writing a file into this folder with a certain prefix. That's it. This is the trickiest slide in the whole presentation, by the way. So I'm going to try to go very slow through it and sort of like explain it a bit. But TPUF is a fully consistent database. So if you do a write in TPUF and you get a 200 back from us, it means that your queries will instantly see that write, no matter what. And this is how we do it. Every time you write, in order to commit that write, you do a compare and swap. You do essentially a conditional write onto this meta.json file. And what you're basically doing is you're going to write, hey, this is the current state of the world. This is all the files that are part of this namespace, as I believe it. And what the cast does, or what this conditional write does, is you say, okay, here's what I think the state of the world is. I might make a change to it. And then if my assumption was correct, if my previous understanding was correct, it'll go through fine. But if it wasn't, if another writer came through and beat me to it, my assumption was wrong, and therefore I will fail, and I will retry, right? And what this means is you have a consistent view of all the files in the namespace. And you can do so without any expensive Paxos or any like weird consistency stuff to handle multi-writers. Please go ahead.
Question that I assume you're going to get to quickly, but do you have a cache layer on top of all of this?
That's the next slide.
Okay.
Yeah, absolutely right. But also that brings up a good point because you actually cannot cache this file.
Yes.
And also, sorry, a little side note here is that like because you can only write this file once per second because of object storage limits, we try to write really, really big batches of stuff. And we've designed our pricing such that it's really cheap to write big batches. And we charge you a lot for writing small writes. It's just sort of a thing here. Caching. And also, before we actually go ahead, is there any more questions about this? Yes.
For those who aren't familiar, can you give a quick overview of what vector searching is?
Oh, sorry, I should have done it way earlier. Yes. Essentially, it's you have let's say like a three-dimensional point, so like 3 numbers essentially, and you're finding what's the k closest sort of like points in space. So a 3D point here, find the closest one. We do this generally in like pretty high dimensions, right? So that was a 3-dimensional example. You can have like thousands of dimensions, generally. Yeah.
Yeah, AWS maps conditional writes in August. Is that different to what you mentioned earlier?
Yeah, the conditional writes is mostly for consistency. So we use it for being able to, for a query, to see results of a write that you just did. If you didn't have this, you sort of would have like basically eventual consistency, which is not what you want. Yeah.
Is cache here on that whole file, as in you compare whether 2 files are identical?
It's the hash of the file, yeah.
Aha, hash file.
It's sort of like, I think in GCS land at least, it's sort of like put if matches hash.
Yeah.
So if the
Of this file.
on this file, exactly.
Yeah.
So
Not-
if this
not
file
the
has
files
the hash
reference
that
file.
you expect, put the file, otherwise fail. Yeah. Does that make sense? I'm going to move on to caching. Yes.
How do you handle these failures? Is it probably pretty common?
Just a retry, right? So you fetch you fail, you then retry, you pull the latest state, and you incorporate your writes into that state, and you try again.
Does that not create a geometrical load when you have a thundering hurt?
Yeah, we kind of avoid that. We generally what happens is that it's like pretty rare to have contention here. We have a consistent hasher which routes requests to the same namespace to a specific node. So that node is usually the only writer. This only really happens when you have like mid deploys where you have like multiple nodes spinning up and possibly having some routing changes. Generally, though, it doesn't really happen that much. Usually, you can kind of assume best case and be fine. Cool. Caching. As you mentioned, you cannot cache that one meta.json file. You need to have the latest state of the world in all queries. Otherwise, you're not consistent. But otherwise, caching is like really, really good in our system. Like it's incredible. We have like 95% hit rate in memory cache. This is like prod data from yesterday. And like 90% MVB. Most requests and most reads we do are cached. And it's like very important that we have like a shit ton of cache for every node that we operate. It's great. Anyway, indexing. It generally helps to index your documents with the search engine. Things that a bit faster. So to be fair, I guess you don't need to. If it's like less than maybe 30,000 documents ish, in that case, we don't even bother indexing. Just exhaustively search everything because it's so cheap to do so that it doesn't even matter. And I'm not going to go too much into details here. It's like very complex. I could talk about indexing all day, but generally, right, our indexing is incremental. That's the biggest takeaway here, is that as we index, we essentially advance a pointer throughout the wall and basically incorporate files into the index. We're not re-indexing the whole thing at once. We're doing incremental updates, and we're essentially writing those changes that people make to the existing index. Very important. And we sort of like, that's the fancy term for it. It's an SP fresh based index. And also we've done a whole crap ton of optimizations on top of that to make it really, really fast and work really well on object storage. Cool. And then as you expect, queries are sort of kind of split into two parts. We have one query, which queries the index. And we have another query, which queries the unindexed portion of the wall. So that's an exhaustive query. We have an index query. Generally, it's sort of 3 round trips to object storage for a query. Our first one is like metadata storage, that kind of thing, like the metadata.json file, the index.json file. The second one is all the index like data, basically we fetch from the index.json, as well as all the unindexed files. And then last but not least, basically all the interesting clusters that we want to explore fully as part of the index query. That's kind of more of a technical detail of the index, but anyway, 3 round trips, and we call that a cold query. So the first, sorry, go ahead, you have a question?
What do you mean by centralized index?
So part of our index basically involves, part of our indexing for vectors involves essentially clustering vectors that are nearby in space together, and then picking a center point called a centroid.
Is it like Ziggy or something more specific?
Have you heard of span before?
Of course.
Yeah, so span basically, so you build clusters,
Yeah.
and then what you do is you do a linear search over the centroids, and then pick interesting clusters to explore.
Mhm.
Yeah.
Do you mind just walking through an example, like a query, basic query that people would understand and how it goes through this?
Yes, for sure. So a basic vector query, right? We're going to first query our consistency layer.
We're gonna query like what would be the name, like what do you,
Oh yeah, so this is like you actually just give a vector, right? So we're doing a key nearest neighbor search for the vectors. So your queries are vectors.
Can you specify the metric, like cosine versus whatever, or it's
You can choose it, yeah.
You can
On a
choose it.
per namespace basis, you can choose what dimension or what this is metric you want to use.
But that's
Usually
like,
cosine or
but that's
Euclidean.
set by the index, right? So I set the data type and then it's like
It's set, yeah, exactly. So whenever you upsert data, you choose a distance vector to use.
Thank
Yeah. But a query essentially looks like you take a vector and you find the k closest vectors, and this is how you do it.
Why are these like why are the things that you're searching for like updated? Aren't like everything's static? And like even if you do update it once, like why would there be contention? Right? Like why would I be querying for something that's like update or something? Isn't this like a low problem?
Yeah, I mean, sort of, there's always going to be new writes, right? So people can still write to the index, like write to the Wolf namespace. And specifically, right, if there's, the tricky part actually is that if there's new writes, for example, if let's say you update document 1 here in like wall 2, and then you update document 1 again in 6, we have to then invalidate the index results based on, because you have a newer version of that document somewhere else.
Brings up a related question I was asked. This files that you're storing in object storage, is it just representations of the index and the vectors, or you're also storing the source documents that the vectors have been calculated from?
Yeah, so we have generally we store 2 copies like of stuff. So all your main writes are stored in files. Basically, essentially what you give us, we store.
So
and then
if someone had text documents they were indexing, they're stored there as well.
Yeah.
Okay. Yeah.
Yeah, and then we would have additional files containing centroids, containing extra index for like full text indexes and that kind of stuff.
Yeah.
two questions. First, is it like deployment officer? So I'm coming from the standpoint of, hey, here's my deployment blue, here's my deployment green, and I update as the purposes. How should I actually use the turbo buffer to update the where I'm indexing, what insertion case?
Yeah, I mean, definitely.
Usually I like build the index 1, index 2, then
Yeah, that's a good choice. I mean, a lot of people, a lot of vector databases have like this idea of an alias, where you like sort of selectively, so you build an index here, you move over your pointer, basically to point to that index. We don't have that natively as a feature, right? Many people do that just by making new namespaces. They're super cheap, and you just like can post to a new namespace and then start using that namespace. And also some people just write a bunch of data into one namespace and then keep searching it. Very challenging to deal with, but yeah.
Do people provide their own vectorizers for the cluster? Like,
Not necessarily. They provide their own vectors, obviously for the actual documents themselves. But we cluster them.
okay, so they have to provide both the document and the vector that goes along with it.
Not even the document, just the vector sometimes.
Okay.
A lot of people upload both the vector and the text, and then index the text with full text search, and then do hybrid queries on us. So they would do 2 queries to us, one for vector, one for full text.
Okay. But there's no ability to provide like
We can't auto embed for you, unfortunately. One day.
so you actually store vector and the metadata to it.
We also do filtering, right?
Oh,
So
you do filter again.
filtering is important. Right? It's like you could say like, hey, I want to find all the vectors closest to this, given that some filter parameter is greater than this, or
On the metadata.
Yeah.
Do you find with the filter cases that you have to do more than 3 round trips to expand the filter material?
exactly that's a really good question. Yes. 3 round trips. I put it at approximate for 3 round trips. Our query planner will sometimes do more. We want to make sure that we have sort of like. It's really important that accuracy maintains really, really high.
What is high?
We shoot for above 90% recall.
Okay.
So we have to adjust how many clusters we fetch and how many we probe basically to maintain that level of recall, especially as the namespace gets larger too.
Yeah, and that recall measurement is probabilistic or statistical, right? Like from the benchmarks, not from.
We do 1% of queries are automatically sampled,
Okay.
and then checked for recall. And then we have a dashboard that sort of like monitors things, and I get paged if they're below 90. So
Also out, but nice.
yeah.
How does filtering impact how many round trips?
Generally, it all depends on the query planner itself. Usually, like the tighter the filter, the less we have to fetch, because we can have sort of the more specificity it is on the filter, we can be sort of like we can fetch less clusters.
Right, so more filtered, less.
But if it's a pretty wide query, right, we want to make sure like we're actually fetching enough data to properly get enough recall. So 3 to 4, usually 3. On our new engine, on our old engine, it used to be more than 4, like kind of 4-ish. Now we're at 3.
Okay.
Yeah. But it does come, just have 4 definitely happens for sure.
But the other reason is that the idea of nearest, when you're filtering, you're like fetching a close neighborhood because normally it will be enough within that density. But once you add a filter, the density of the neighborhood changes, and you sometimes have to go further outside to get more data to have enough results for your K. Here's like K
Right.
is larger.
Right, that makes sense.
Those are good questions.
So,
Yeah, you
so
absolutely
your filters can make the query less or more expensive than the filtering more. That's pretty hard to optimize.
to make sure that we have 90% recall. It's like absolute paramount that we like. It's like we can get you instant queries, but they're like we need cool. And generally latency wise, right? Our cold latency, our cold queries, aka completely uncached, the first time you query a namespace is going to be slow, right? We're roughly like have 336 milliseconds ish median latency. Not great, but we very quickly cache everything we can, and our latency drops to roughly 17 milliseconds ish for a 1 million document namespace. And what's neat is that this is the exact P50 of GCS. So that's the exact P50 of us doing 1 round trip to query that consistency file. And we completely mirror GCS in this part, which is good. If it's more than 17, it's bad. And again, if we want to get faster, we don't have to fetch the consistency file. If we allow eventual consistency, this can be much, much lower. We get down to single-digit milliseconds. I think we've been really careful about doing this. It's a Boolean. We have a single function that was toggle like this. certain customers, it makes sense to toggle it. For now, we just keep it strongly consistent for now.
So the cache hit, like it hits in the in-memory cache or the SSD.
Yep.
And if your same P50 as GCS, does that mean that anyways, what I'm trying to ask, I guess, is that you mentioned that if you don't hit the metadata file, you can get in a few milliseconds. You do hit the metadata file, it'll be similar to GCS. So you're clearly doing some optimizations.
Yeah, so we pipeline and prefetch things. I think the trick is we kind of like we assume that we're during query, it's like all this like massively pipeline thing where we fire off stuff, assuming that we're correct.
Right.
And then redo it if we're not. A lot of the time we are correct, right? Like I think for like 95% of the queries, whatever, we can basically start doing the query, assuming a stale consistency file, and then just wait till the P50 the query returns and make sure we're correct and then just turn the results there.
Makes sense.
Otherwise, we have to wait and redo it. But the normal P50 case is just checking that we're okay and finding it.
Do you have a cache eviction problem ever?
Not really. All the files are mutable on object storage, right? So as long as you write down, you're good. And we don't really have a cache clearing mechanism. We just have like caches remain until they get evicted, usually like within 2 or 3 days sort of thing, depending on how often we deploy and whatever. Yeah.
Good question. If I understood correctly, so you first check the metadata file, and if nothing has changed, then you read from cache, right?
We kind of take the faster route is that we assume that we're correct. We read from cache, we do all of our proper work.
And then make sure.
And then as soon as that query returns, make sure we're correct.
Gotcha.
And if we're not, we can retry.
And does your metadata file increase in size the more you insert into the database?
Yes. We up until last week, we have never deleted anything on our wall. We are doing compaction now, which is a good thing. And it kind of helps sometimes. But yes, these files are kind of big sometimes. So I think our biggest one is like 200 megabytes ish, which is really bad.
Are there any issues like with like hashing that quickly enough?
Yes.
Okay.
How do you check with LSM then? Or like, how do you like the actual?
So as long as you fetch that file,
Yeah.
you know that you're looking at the exact correct, all the rights have been.
So committed into some substance as soon as I fetched it. I'll do it.
As soon as you have a non-stale version of the
Oh, I
file that you just fetched. Yeah, exactly. Cool.
And you fetch the entire, like the metadata file, all of it's in memory, not a portion of it.
Metadata file, yeah, it's like all queried.
Yeah.
There's optimization you can do in GCS at least, where you can essentially like, only return the body if it changed from a hash. So if you know that current hash,
Yeah.
you just instead of them telling us. Yes, many people just sort of generally use an attribute to represent that. Right? So they'll upload multiple turbopuffer documents and then have some sort of internal ID attribute on those documents where they can sort of do more. We don't handle it. I think people would like us to handle it. I think it's one of those things that like customers can generally work around. So we try to kind of punt it off on them for now. I think it's better for us to work on the core retrieval problem and then slowly sort of expand into those areas once we know more about it, kind of thing.
Can I ask one bizarre question?
Yes, please go ahead.
Say I'm like here on red with some fine cover, and let's assume that the elastic at some point will get there together. Why should I go to turbo buffer?
I mean, good vibes.
Can agent bake copy?
I mean, definitely the Elasticsearch, right? I mean, it's really good at full text search, right?
Yeah, exactly.
If it's low latency, right? If you have a really like massively online data set, if you're Shopify, for example, right? You're not going with debuff right now. You need instant search results. It's also one big giant index, and we suck at that.
Let's say I need to sell you to my manager. What's my take? Hey manager, we really need those guys.
Do you have lots of small namespaces?
Oh wait,
That's the question.
I do databases. I was doing this first before.
Okay.
How did this way? He said how different from this game? Because this game is source.
Yeah, I mean, Disconnect is. I don't know. Again, I don't know too much about it, but for our purposes, we did an expensive experiments with Disconnect. We also tried HSW and different other algorithms. The nice thing about span and how we did SP Fresh is that it maps really, really well to object storage. So when we're fetching clusters, each cluster, you can just fetch them all in parallel at once and maximize your bandwidth from object storage. So the sort of the clustering approach looks really nice in object storage because you can all do it in one round trip. So centroids and then fetch all the clusters, done. Yes.
How much time do you spend on trying to find like a really good hash function for your metadata? Because there's some really fast ones out there. Is that something you're trying to optimize as well?
I don't think so. I mean, we mostly just sort of like have to. A lot of our hashing generally comes from like doing etag, like MD, like it's like MD5 for GCS. It's like pretty cheap hash functions, nothing crazy.
Gotcha. Are there any? I guess collision is unlikely. Never mind. Yeah.
Yeah, and like certainly, definitely, like we do some hashing and stuff at the wall, but yeah, not a huge portion.
What's a really bad use case, like, for example?
I mean, I think yeah, like just what I mentioned earlier, like a Shopify example, right, where you have one massive index that's queried constantly. That is much better served by a sort of a memory database, right? Like a proper in-memory, non-sharded database, right? We would
Multi-tenant, so wouldn't that be multiple lasers?
shops, yes, but like for example, like if you're doing the shop app, we have like one giant index, you're switching over all shops. We suck at that. I would love to power like Shopify itself. But yeah, that would be sick. Yeah, that's the kind of the problem. We're pushing now into, as of last week, we got 100 million in one namespace working pretty well. We're sort of like pushing it pretty heavy. We're trying to get to 1 billion, like in the next like little bit, but those big namespaces come up with a lot of challenges. It takes time.
A question about your LSM tree for the index.
Yeah, but
How are you getting any segment elimination? If you are, how are you organizing it to maximize segment elimination?
what is segment elimination?
Like not having to download all the different segments in the LSM.
Oh yeah, okay, yeah. We fetch all the index blocks.
Okay, so you just full scan it all.
We full scan the index blocks and then we just fetch the blocks we need, the data blocks we need. We try to keep the index blocks pretty small, generally.
So the LSM tree can be like, what's the main use case for the layers in the tree?
I mean, generally, having the layers means you can get back things pretty tightly. And like the problem is also the big thing about your storage amp, right? Like anything we do to your storage application in our index is like really, really good. It costs us a lot of money. These are like very like hundreds of gigabytes namespaces. So compacting it also means that we get more bang for our buck when we do a query. We get more like sort of like tightly coupled data. So if we can like have a really tightly compacted index and fetch it all in like chunks, basically, we're kind of having a good time.
The LSM tree is basically mapping from like cluster ID versus like a vector to like a list of segment and contain a vector, like wall files and contain that cluster.
We embed to avoid the extra round trip, we embed the vectors themselves in LSM. Yeah.
Oh, okay. That's
But it's towards the value, but yeah. You could also theoretically make it a pointer into the wall. It's just a super reasonable approach, yeah.
Since it's not a local database, what is your testing strategy?
We do have tests. It helps the databases. They don't like it, we don't have tests. We essentially have a test account that we use, and we just spin up a bunch of namespaces. So like each test has its own namespace. And we just do everything from there.
So that's end-to-end. What about some integration?
We definitely have like integration tests, right? That do like GCS operations, that kind of thing, right? But it's all like basically namespace and prefixed by the function name of the test. So you can kind of do them all at once and just don't have collisions really.
No wild torso simulation or anything like that.
One day.
Yeah.
One day, yeah. There's also like antithesis, which you want to try eventually, but one day. It's really expensive too. So.
That's the way that's hard. Like, infinitely configuration.
Yeah.
Reducing that to something you can finish in the amount of time that we need a process.
Yeah, I think generally, I think we generally try to focus on like proper end-to-end tests, right? I think that's sort of like all you can really do. There's some tests that we do really specifically, but end-to-end's the way to go for sure. Cool.
I love that Morgan's touched on query planner and indexes because I'm gonna touch on that too, and that's a good start of the story. My talk is going to be quite MySQL specific, but I hope you'll enjoy all the ins and outs and the little details. Some of this is relevant to Postgres as well, but not all of it. All right. So we want to design some sort of a reservation system that lets you for like 9 years. Worked on various stuff of infrastructure, moving from data center to cloud. Lately, some M&A and some database work as well. All right. So we want to build a reservation system, and we want it to be ACID compliant and basically to live in the same relational SQL database that we run for a bunch of good reasons. And for this reservation system, we have a limited amount of stock for each item, and we want to be able to sell it out quickly at the high load without underselling or overselling, because that would make people unhappy. And the requirement is to build this within the same database that we run, which is relational. Not considering something like Redis encounters here and decrements in those counters. So there is let's pretend we're using this schema. Two tables. One table with available tickets represents available tickets, and single row means there is a single ticket available. So if there's 1,000 tickets, we insert 1,000 rows into there and let people grab them from the table. And then we use another table with the reserved tickets just to kind of keep track of the fact that someone grabbed a ticket to be able to do some bookkeeping later. We can use a pretty neat feature available in MySQL and Postgres on select queries that's called skip locked. And we use it in combination with for update, which lets us lock the rows that we're grabbing from the table. So they're immediately unavailable for other transactions to be modified. And we also use like for update locks the rows, and skip locked makes it so that it doesn't wait for the locks to get released on rows that it can see at the beginning. So every time you do that select from available tickets, MySQL would traverse the B tree in that order that you specify. Basically, and if you're passing limit 10, that means can I get 10 tickets, please? And it would traverse the beginning of the B tree for enough to get enough rows, skipping those that are locked. Which is a pretty neat trick to make this as concurrent friendly as possible and to avoid different transactions interlocking on the rows that other transactions are working on. Yes.
What do you mean by lifelong security? What would happen across that?
Whenever a select hits a row that's locked by another transaction, it would be waiting for the lock to be released by that other transaction, which might take a while, or it might even cause a deadlock if there is a deadlock situation there. So after we execute that select, we check on the client that we actually got 10 rows, because it's possible that there is only 9 tickets left and limit 10 will give us only 9 rows. In that case, if that customer wants to get 10 tickets, we can satisfy them, or like we can introduce some logic, still sell 9 tickets if we only have 9, depending on the business logic. And then we do an insert into that bookkeeping table, and then we delete those rows from the table that represents locked and available units, and then we commit this transaction. And all right. And this works quite nicely as you increase concurrency. But having just a global pool of tickets does not really work. We want to have like events. So we can introduce a column called event ID. And whenever we select from available tickets, we also specify where ID equals the foreign key.
Question. Let's be understanding personally, because I didn't really queries, but so when you do a select query, because I'm saying everything that you selected from will be locked throughout the lifetime of that query on the comments.
Yes,
Okay.
those rows are locked for the lifetime of the transaction.
Okay.
And we do that delete so that those rows are no longer there
Okay.
after the transaction completes. And like by making these transactions as fast and with as few round trips as possible, we make them hold those logs for less time.
Does MySQL not support the delete return?
No,
Okay.
it doesn't support insert return either. So we introduce event ID as a dimension. It all works fine. And then the next thing I'm kind of getting into is that MySQL has this pretty neat meta table called data logs that lets you inspect all the rows and stuff that is locked during your transaction. So you can do a begin statement, do some queries that are part of your transaction, then inspect the table and verify that you're not holding locks on more things than you want to. So the moment we introduce event ID, we see there is two locks there now. One is on the event ID index, and another one is on the primary index. And that happens because MySQL now needs to lock on kind of both dimensions. First, so that those primary keys, so that no one can modify or delete those primary keys, and also on the event ID index. And that's more locks in memory, and we want to have less locks, right? So we can.
Question: what is the rec? View back slide. What does the rec not gap mean here?
It means that it's not a gap lock, and the gap lock is when it's a lock on a range.
I see.
So that means that it's on a single row, which is good for us. If that where event ID was a range instead, we would see a range lock and a gap, essentially a gap lock.
You're putting like estimates on like at what type of throughput did you have to start caring for these?
I think I don't have a specific number, but like as we iterated on this approach, we tried to make the basic unit of work, the basic like reservation operation, as cheap as we can get. And maybe holding more locks in MySQL memory is not really a bottleneck, but like why not optimize it? And I'm going to get to the way that's pretty easy, the way to optimize it. So if we think of how the data is stored on the B tree in the database, there is a B tree with ID as a primary key. And then there would be a B tree for the event ID index that we've introduced. So whenever we want to grab rows by event ID, we need to traverse both B trees, which causes the locks. But if we use composite primary key, that makes rows under the same event to be collocated on the disk so that they're on the same page. So there is a few wins here. One of them is that it's quite likely that to grab few rows from the table with a composite primary key, you need to only read fewer blocks on the disk. And then another advantage is that that makes us reduce two locks into just one lock, which is pretty great. And just like in general, this performance schema data logs table has been super useful for debugging other things to make sure that, say, something is not causing a gap lock on too wide of a range during other operations that we've been trying to scale in combination with this feature. Okay. And we're slowly getting to gap blocks here, actually. So now pretend we've run out of available tickets. And whenever someone tries to select from that table, they get in zero rows. With the default isolation level in MySQL, which is repeatable read, MySQL has to guarantee that whenever you do another select here, it returns the same empty set, which causes it to hold a lock on that whole set to keep it empty from other transactions being able to insert, which sucks for us because say someone's credit card did not go through, we want to return a few tickets back into the pool. But we now cannot do that because there is a lock on that, and that's how you can inspect it. It's labeled as supermoon pseudo record, which I think is MySQL's slang for a lock into the infinity of everything that you insert. So we would see things. Oh. So whenever we would want to what we call replenish that pool of tickets, we would see things holding on the clock. So the solution to this was pretty easy. Relax the isolation level to read committed, which no longer guarantees that same select would return same empty set. So we're good here. And the advantage here is that you can relax that just on a single transaction that you're running, because changing the isolation level for a big app can be a lot of work. Okay, now.
Any change it for this on the table?
No, it's set either per session, which is a connection, or per transaction that you're starting. Okay, now we're getting into the query planner bit, which is super interesting. So after we acquired those rows that we have locked, we're deleting them from the table, and we would see that query run into deadlocks because as we try to use the tools that are available, we would see that a delete for the different range of IDs would somehow be deadlocked on delete of another set of IDs, which did not make sense. So you can imagine delete from where ID in 1 and 2 would be deadlocking with delete where ID in 3 and 4. And that was super puzzling until we found this bug in MySQL. And I'll get. Okay. And the idea is that when the table is small enough, the query planner decides that it's way cheaper to walk through the whole table than find those rows by primary key. So say this table is 100 rows and we're passing like 20 rows here because we're asking for 20 tickets there. It's like the planner would start thinking, okay, the table is 100 rows total. We are selecting 20 rows. It's rather than navigating the B tree so many times, it's easier to just walk through the whole table. And as many transactions would be walking through the whole table at the same time, they would be locking on each other.
What sort of arbitrary value do you find this switch in per size?
I think it's at the scale of thousands of rows. And the bug actually mentions it. And your table is very small, so it's much more efficient to scan an entire table. This is behavior by design, which is kind of like, why? This is so annoying. Like, I'm optimizing things to lay and to operate with a table the same way that it's physically located on the disk as a B tree. And I expect like kind of the same performance and guarantees, but the query planner is non-deterministic because it's kind of, you could say that it's optimized for 50 of queries that people run on MySQL, but not for P99. And we're here in like P99 territory. And when I say by P50, it's like often when people run queries that they are not even covered by an index, or maybe just like the first part of the where clause is covered by an index and the rest. So the optimizer tries to be smart, and that's like how what people might want from relational databases often.
Behavior by design is to ignore force index.
So you can't do force index on delete.
Okay, yes.
And they've considered it, but it's like too big of a change or something. Yeah. And then we get.
Is this MySQL specific, do you know, or do other?
This is very MySQL specific, also because of like quirks of its planner, and that planner is specific to InnoDB as a storage mechanism. And MySQL is unique in that way that it has pluggable storage mechanisms. So in Postgres, there is only single storage mechanism. And
something similar exists.
It is a pain in the ass to get relates on row like the row of there's also the SQL Server and all that, and pretty much every standard everything else you think of, because they're designed with all those one this and each have to do and then kind of like carries over.
But you can plug in your extension with the right.
yeah, way easier to write extensions for Postgres. So getting back to this table, again, as I said, super useful for any sort of performance work on MySQL. In fact, there are tools that are popular in the ecosystem that check the table like every 30 seconds, report that as a tool, and that's like a SaaS software that you pay thousands of dollars, which is super useful. We use that too. Unfortunately, looking up the table can lead to excessive memory usage. And it was fixed in the latest MySQL version that only came like a couple months ago. So before that, it's kind of like no one noticed much. And it's more likely to cause OMS if it's hitting queries that operate with a lot of rows. So like we would find a query that's touching tens of thousands of rows, which is not great, but like queries like that happen once in a while, in a big app especially. And we would find that hitting that performance schema around in the same moment as some larger queries are running would lead to this. Thankfully, because here it's like you can see status not a bug, which is how they mark many bugs on MySQL issue tracker. Thankfully, this one was marked as a bug. Should have a screenshot of that. So, okay, takeaways. First, preferably avoid software that's run by Oracle. Outside of edge cases, this is working pretty great. Like we would get it to tens of thousands of reservations running per minute. And what's great is that you can, like, if a single user is asking for 10, you can batch reservations from a few users, ask for 100 for 10 of those, and that drastically allows to boost up the performance. Yeah, and the query latency for that whole transaction stays under like half millisecond, which is great. And this is essentially a blog post that I wrote not that long ago. There's a couple of them. Maybe you'll enjoy reading, and this is pretty much it for me.
Don't get me bullied on the spot. you work at Shopify, I work at Microsoft. While I was thinking, I have this board in mind a few places, a few times in-house. Why didn't you patch it by yourself?